First, in order to prove the bound, the upper bound on the number of cameras needed on a simple polygon, we are going to prove it. It's based on the triangulation of a polygon. So we are going to decompose the polygon into triangular pieces. And first, let's try to ask this question: if I decompose this into triangles, if any simple polygon, given any polygon, if I decompose it into triangles, how many triangles are there going to be in this polygon? N over 2, N over 3. So if I just generate triangles, if I just divide this into triangular pieces, when I say triangular pieces, the triangles do not intersect with themselves, and the union. Yes, corners of the triangles must be the vertices of the polygon, and this should be. I mean, we shouldn't introduce new vertices in the middle. Okay, we should be able to triangulate this by using only the vertices of this polygon, no additional vertex inside the polygon. So in such a triangulation, how many triangles would there be in a polygon of m vertices? Any guesses? Okay, yeah, that's a good guess, but actually the actual number is a lot higher. Any simple polygon, it's an exact number. There's no minimum or anything. There may be many different triangulations. Okay, there's no unique triangulation. You can triangulate the same polygon in many different ways, but one thing is common in all these triangulations is that there are exactly n-2 triangles in your triangulation. Okay, so it's always n-2. And we are going to first prove this. There's n-2 triangles in any triangulation. And the proof is by induction, but it's a really nice proof that I want to do it here. By induction, first our base case is a polygon with the smallest triangle, which is n is equal to 3. When n is equal to 3, there is only one triangle. So n minus the number of triangles, 3 minus 2, one triangle works for the base case. Okay, for n is equal to 3, we have one triangle that works for the base case. Now, the induction is really a nice induction. It's going to prove that there are n-2 triangles in a polygon. First, let's assume that we have a polygon with m vertices, so let's assume actually for n, so this is the base case and induction hypothesis. If n has n-2 vertices, n plus 1, a polygon with n plus 1 edges is going to have n-1 triangles, not vertices, sorry, n-1 triangles. And the proof is actually using the proof. The proof does is, the proof for any polygon of size n, or we can do vice versa actually. If it's true for n-1, if there are n-3 triangles in n-1, we are going to prove for a polygon with m vertices there are n-2 triangles exist. And the proof actually is proving that any simple polygon n has a diagonal. Okay, it actually proves the existence of a diagonal. Okay, so let me first define a diagonal. What's a diagonal? A diagonal is a line segment that connects the two vertices of the polygon, two distinct vertices of the polygon, and the line segment completely is inside the polygon. Okay, you are going to a diagonal, for example. This is not a diagonal. For example, connecting these two vertices will not give you a diagonal because the line segment you draw is not completely inside the triangle, inside the polygon. For example, this is a diagonal. Okay, so we connect these two vertices, and the line segment is completely inside the polygon. So this is a diagonal. Now, what we are going to prove is that any simple polygon of n vertices have at least one diagonal. Okay, we are going to prove the existence of a diagonal. Okay, and after we can prove the existence of a diagonal, the induction is going to be very simple. Now look at this observation. If there is a diagonal, this diagonal divides the polygon into two pieces. And how many vertices these two pieces have? For example, it may be M1 vertices, the first half has, and the other half may have M2 vertices. And what the relationship between M1 and M2 is that if there's such a diagonal, if these are the number of vertices in the two different parts that the diagonal divides, here we see that these two polygons, these sub-polygons, share these two vertices, right? Okay, so I can actually summing this up and dividing the two shared vertices, what I know is I'm going to get n. This is equal to n, right? If there exists a diagonal, and if this diagonal divides my polygon into two pieces with m1 and m2 vertices each, m1 plus m2 minus 2 should be equal to n, because this part, if it's m1, these are the two shared vertices. If I add up the vertices of these two sub-polygons, subtracting the shared polygons should give me the total, the original number of the whole polygon. Okay? I mean, if you can prove the existence of a diagonal, of course, if such a diagonal exists. And this diagonal can be dividing the polygon, for example, into almost equal halves, or it may divide the polygon into a smaller polygon and a large polygon. We are not interested in the actual numbers of m1 and m2. m1 and m2 may be close to n over 2, n over 2, or it may be n minus 3 and 3, for example. Okay, in this case, one of them is 3, the other is n minus 1, right? Yeah. So it may be here, if I have this diagonal, m1 is going to be n minus 1, because I'm only missing this vertex. Okay, if this was my diagonal, if I divide the polygon into two, in this large polygon, I'm only missing this vertex, so the number of vertices in this polygon is going to be n minus 1, and this one has 3 vertices. It's going to, subtracting 2 from this is going to give me this. Now, having done this, and what I know is that m1 and m2 both are what? Smaller than n. Okay? So hence come our induction using the hypothesis that I'm not going to use n minus 1 only in this induction hypothesis. I'm going to use for any number of, for any polygon with vertices less than m, this is true. Okay? This is what the induction says. Prove it for the base case, and for a polygon with n vertices, assume that for polygons with smaller than n vertices, this holds true. This theorem is true. So the thing is that if we can divide the polygon into two pieces with m1 and m2, we assume that this is true for m1 and m2. So the number of triangles in a triangulation of this part of the polygon has how many triangles? m minus 2 triangles. m1 minus 2, and the number of triangles in the other part is m2 minus 2 triangles. So these are coming from my induction assumption, okay? I assume that this is true for polygons with less than n vertices. So there are this many triangles in this small sub-polygons. So what are the total number of triangles in the combined one? I sum these two, and what is this? m1 plus m2 minus 2. What is it equal to? This part, n, right? This is what I gave here. So it proves there are n minus 2 triangles in the combined polygon. Okay, now the part of the proof that we didn't complete it is that, does a diagonal always exist in a polygon? So we need to prove the existence of a diagonal. If we prove that part, the proof is complete. Now, it is done like this. We select the leftmost vertex of a polygon. I mean, this picture is not very, okay, it's like this. Let's assume we have this room is slightly like this, okay? So I'm making this the leftmost vertex with this floor plan. So we select the leftmost vertex of the polygon. If there are more than 2 polygons with the minimum x coordinate, I select the one with the minimum y coordinate. Then after I select this vertex V, I connect its neighboring. So it has 2 neighboring vertices, right? Since this vertex is incident to 2 edges, it has 2 neighboring vertices named U and W. I connect this U and W. Okay? So, in my example, it's really good. This UV, the line segment UW, does not, if it doesn't intersect with any polygon edge, what it means that you have found the diagonal. If it intersects, imagine now this part is a little bit longer like this. Okay? If it intersects, then it's not a diagonal. What I do is I select, so there are 2 vertices here. Let's name V1 and V2. If it intersects with some edges, it means that some vertices lie to the left of this line segment UW. What I do is, out of these vertices, out of all the vertices that lie to the left of UW, I select the one which is farthest away from UW. So I compute the distance of V1 and V2 to the line segment UW, and I select I connect this one to my V. Sorry, it's a line. The farthest vertex found here is going to be connected to this leftmost vertex, and it's going to give you for sure another diagonal, because there can never be any other vertex closer to V than this V2, because you chose this V2 so that it's the farthest vertex from UW line segment. So you guarantee that this line segment you draw between V and V2 is going to be completely inside the polygon. If it's not inside the polygon, it contradicts with our definition of how we select it. If it's not the farthest one, it means that there's another vertex behind it, so we select it in the wrong way. So if you select the farthest vertex, farthest to this UW line segment, you're always going to be able to find the diagonal between V and this farthest vertex V2. Okay, so hence in both cases we prove, it shows that we can draw a diagonal. Okay, if you can draw a diagonal, it means that you can split your polygon into 2 pieces with smaller number of vertices, and hence by induction we are going to have n-2 triangles in the final polygon. Now, after this also, actually this proof is a really constructive proof showing how we can triangulate polygons. Okay, we can use the techniques we used in this proof to triangulate a polygon. I mean, just adding diagonals always from the left side. As soon as you added a diagonal, remove this triangle from the polygon and do the same thing for the remaining part. Okay, so all you need to do is starting from the leftmost vertex, find this diagonal. If finding this diagonal is actually not always going to give you a triangle like this, sometimes it's going to divide the polygon into 2. It may be 2 different polygons. For example, if my diagonal is in this picture, if the diagonal I drove is this diagonal, if you are going to find a triangulation of this polygon, As you can see, this diagonal does not give me a triangle immediately. All it does is it divides the large polygon into two pieces. Okay? But I can use a divide and conquer approach. After you have this diagonal, then triangulate the subpolygons. So triangulating this will be the next thing to do. So this is, to triangulate this, this is the leftmost vertex, and these are the two neighboring edges. And when I draw this one, I see this vertex is to the left of it. So what I do is I draw something like this. So it's a very thin triangle, but it's again divides the polygon into two. And the second divided part is already a triangle. So this is, in this divide and conquer approach, if you are left with a polygon with 3 vertices, it means it's already a triangle. That's your base case in the recursive call to this triangulate function. And then we are left with this by drawing diagonals. So actually, triangulation is nothing more than drawing diagonals, okay? So our goal is to draw diagonals each time, and each drawing a diagonal is going to reduce the polygon into pieces. And at the end, we are going to have ourselves a triangulation of the whole polygon. Now, what is the complexity of this algorithm? The complexity of this algorithm, if we analyze it, turns out to be n squared. Okay? Because in order to find this farthest, no, we are first finding the leftmost one, and we are going to do this finding the leftmost one n times. And in order to draw this diagonal, at the worst case, we may need to, if all the vertices are to the left-hand side of this UV line, we may again need to find the maximum of these vertices that are to the left of this UW line, so line segment. So this algorithm you'll be able to generate triangulation of any simple polygons in O(n) squared time. But now we are going to see an algorithm in which we can reduce this to n log n. So we'll be able to triangulate any simple polygon. Actually, our algorithm that we are going to describe is a generic algorithm that it can triangulate polygons with holes, okay? And if a polygon has holes, this n log n is an optimal approach. But actually, people have worked on this polygon triangulation a lot, many researchers, and there are algorithms which, given a simple polygon, you can triangulate a polygon in O(n) time. Okay, so even you can reduce this n log n. Today we are going to see an n log n algorithm, but there are algorithms, this is a randomized algorithm, which can triangulate any given single polygon in linear time. We are not going to see that algorithm. I'm just, if you're interested in polygon triangulation, you may read that algorithm as well. But today we are going to see an n log n algorithm. And this n log n algorithm is going to first decompose the simple polygon into what we call monotone pieces. This is going to take O(n) log n time, and a monotone polygon can be triangulated in O(n) time. I'm going to define what monotone is shortly. But before we describe our triangulation algorithm, let's again try to relate the triangulations to our first initial problem, art gallery guarding. So if our polygon is now composed of triangles, okay, if I have many triangles like this, okay, so I mean, I'm going to use the picture in the book. This is a complicated polygon here. I'm going to describe this on a much simpler polygons. But the thing is, after we have the triangles, how does it help us to prove this tight upper bound? Okay, if you have a polygon composed with triangles, where do you place the cameras? First of all, one thing that you can do is you can place a camera. Since each of these triangles is a convex polygon, you can place a camera at the center of each of these triangles, which is going to guarantee you are going to guard the whole thing. But the bad thing is the number of triangles is n-2. So if you place a camera on every triangle, you are going to have n-2 cameras. But do you really need n-2 cameras? The first thing you see is that if there are two neighboring triangles, if they share a diagonal, if two neighboring triangles, if you place a camera anywhere on this diagonal, you are guarding both triangles, right? Yeah, instead of having two cameras in two triangles, you can put your camera here on the diagonal, which is going to make sure that you're guarding both triangles completely. So now we can reduce it to maybe n-2 over 2 if, for all shared triangles. But can we do better? And the answer is yes. It's like this. Imagine all the triangles here. I mean, instead of placing it on a diagonal, actually placing the cameras on vertices is a better choice, because a camera that is placed on a vertex guards all the triangles that it's incident to. Okay? I mean, if this vertex is incident to a triangle, it's guarding all the triangles that it's incident to. This vertex, if you place a camera here, I mean, don't forget, our cameras can see 360 degrees. I mean, imagine they're rotating, okay? So if I place the camera at a vertex, it means that it guards all the triangles that it's incident to, because it's seeing, since it's a part of this triangle, it means that I can draw line segments to inside of this triangle, and I'm going to see it. If a vertex is incident to a triangle, it means that it guards that triangle. If you place a camera on that vertex, you are going to guide it. Now the question becomes, can we select a subset of these vertices so that each triangle has at least one vertex in this subset? Okay, so the problem becomes this. I mean, we have this many triangles. Our goal is to select a subset of these vertices so that each triangle is going to have at least, it's like a vertex cover problem, but it's like, I mean, maybe this is how they found its MP hardness. I mean, this may be the problem that they reduce. They may have reduced vertex cover to this problem, because it really much looks like a vertex cover problem. I mean, selecting a subset of vertices to cover all the triangles. Okay, so what subset? So the exhaustive search would be to look at all the subsets of vertices, which is 2 to the n. So it gives you an exponential algorithm if you try to look at all the subsets of vertices that cover all the triangles. But an approximation, it's not an approximation, but an algorithm named tree coloring of a graph will help us to select a subset of vertices which are not going to be larger than this number. Okay, so with this idea, we are going to select a subset of these vertices among our triangles, and we'll be able to select no more than n divided by 3 vertices. So this is done by using a strategy called tree coloring. And tree coloring, we do the tree coloring of the dual graph of these triangles. It's like this. Actually, we are going to color the vertices of the triangles. And each vertex, and the rule is like this. If you have many triangles, so for example, let's look at this one. We have triangles here. Okay, I mean, in this example, the minimum number is 1 for sure, but let's have other triangles as well. Okay, now our goal will be to give colors, 3 different colors, to the vertices of triangles, and the constraint is that this. If a vertex is colored with a certain color, all the other vertices that share an edge between this vertex should be colored differently. Okay, so for example, if I color this black, this should be either white or red. So these are my three colors, black, white, red. So each vertex of a triangle should be different colors. That's a basic conclusion out of this constraint. If you have a single triangle, all its three vertices should be of different color. And also, if considering two triangles sharing the same diagonal, okay, if you color this black, white, and red, the color of this vertex is also specified. It cannot be red, it cannot be white, because our constraint is that two vertices that share an edge should be colored differently. So the only thing that left for me is to color it black. Okay, so, but the question is, really, does it tree coloring always exist for any triangulation? Is it possible, I mean, to tree color this graph? And the algorithm that we are going to show you shows that it is possible. What we are going to do is, for any given triangulation, so this is our triangulation, for example. We are going to construct a dual graph of this triangulation. And actually it's going to be a tree, we are going to show that. And it's like this. For each triangle, we are going to have a node in this dual graph. And we are going to connect, so these are going to be our nodes. And we are going to connect two nodes, two triangles, if they share a diagonal. So we are going to connect these two, these two, these two, these two, these two, these two are shared. Okay? Actually, yeah, this is not a valid triangulation because I put a vertex in the middle of my, so that's why it's not a tree. If we had, so this vertex actually is not allowed in simple polygons. If you have a simple polygon, this vertex is not part of the polygon. So what we can do is something like that. Let me change this to something like this. Okay, let's make it a vertex of the polygon. So this, now it's the vertex of the polygon. And I can even do it something like this. Okay, and a diagonal is this. And also, this is also, we are going to have problems with, let's assume also there are no collinear, so it's, let's have it like this. And let's have it, so I have something like this. Okay, so now, I need another diagonal to do that. So in order to make it a triangle, I need another diagonal. Now we're done. Let's make this straight as well. Okay, now we have a triangulation, right? And let's have the nodes. So any two nodes, triangles that share a diagonal, we are going to put an edge between them. We are going to put an edge between these two as well. And that's it. Okay, so this is the dual graph of our triangulation. And this dual graph is actually a tree because each diagonal here, since it splits our polygon into two pieces, it splits our graph also into two pieces. So if removing an edge from a graph always splits the graph into two pieces, it means that the graph is a tree. There are no, okay? So here, this dual graph is a tree, and the tree coloring algorithm is based on a simple traversal of this graph. And it's like this, we can either use a depth-first search, I mean, we can traverse this tree either using depth-first search or breadth-first search, any way you like. But the thing is, you need to traverse all the nodes of this tree. So it's like this. You start with any vertex. You start with any node on this graph. Start with this, for example, or this. when you start with this node, you color all the nodes with different colors of this vertex, so black, white, red. And when you're traversing this, you go to the next node, the remaining, so since the next node is sharing a diagonal with the already colored triangle, the only thing, what you are going to color the remaining node is already given. Because since you have colored these with red and white, you are for sure that this node is going to be black. Okay? So you label this as black. Then from this node, you can either go this way or this way, based on how you define your left child, or how you're going to traverse. It doesn't matter. Okay? It doesn't matter. The thing is, in this depth first let's go this depth first, for example. So when we go this, the shared diagonal, these are red and black. So this is going to be white. Okay? And in this traversal, since we have reached the deepest node in this branch, we go back and we follow the other branch in this depth first traversal. And we go to this one, and this one, the shared diagonal black and white, so this is going to be red. And we continue following the next node in this traversal, black and red, so this is going to be white. And the final node, white and red, this is going to be black. So by using this strategy, you'll be able to traverse, after you traverse the whole tree, you are going to have yourself three coloring of the vertices of this triangulation. So why do we do this three coloring? Is that by selecting let's look at the colors here. How many blacks we have? 3 blacks. 3 whites, 2 reds. It means that if you place your cameras on these red vertices, these red vertices, what is their property? They cover all the triangles. Okay, so since these reds, these 2 vertices, they are incident to all the triangles in our set. So therefore, hence this bound comes from the 3 coloring. The smallest of these 3 colors. If you have n vertices, you divide it by 3. One of them is going to be n divided by 3 floor. Here in this case, we had 1, 2, 3, 4, 5, 6, 7, 8 vertices. So 8 vertices divided by 3, floor it's 2. So it's possible to guard this simple polygon by just 2 cameras placed in these colors, which is the smallest one. Okay, so this is how we can always say that we can guard any simple polygon with at most this many cameras, of course, if you can triangulate it. If now the remaining thing is how we are going to triangulate the polygon, then this is the final topic of our today's problem. Given a simple polygon, how do we triangulate it? After you triangulate it, you can, by using this 3 coloring algorithm, you can find where to place the cameras. Now, for triangulation, we can use the O(n) square algorithm, but now we are going to see an O(n) log n algorithm, which is based on first decomposing our simple polygon into what we call monotone pieces, and specifically Y monotone. So this is what monotone means. So I'm erasing this part. Mm-hmm. Mm-hmm. Convex polygon, for convex. So, okay, the thing is, yeah, making it, why don't we make it a convex polygon? For example, make trapezoids. Not, why do we triangulate? Let's do trapezoids, it's going to be better. The thing is, it's really difficult. There are algorithms, people have search for algorithms to divide a polygon into trapezoids or other things, but they're very difficult algorithms. So in general, decomposing a polygon into convex pieces, and these convex pieces may be of any number, is a difficult problem. So triangulation is an easier problem of all these other type of problems. So, and it can be done in linear time. So a simple polygon can be triangulated in linear time. So that's why we do it.
Yani poligonlaştırsaydık daha az kameraya
Yes. No. There can be less cameras than this. This is an upper bound. Okay, there can be and the minimum number of cameras is NP hard. So we cannot. And it also shows that maybe decomposing it into a maximum smaller number of convex polygons. It also says that decomposing a simple polygon into a smallest number of convex. Decomposing a simple concave polygon into smallest number of convex pieces is also NP hard, right? I mean, because you can reduce one problem to the other easily, because if the minimum number of convex pieces, if you put one camera into minimum these, it means that these are also the minimum number of cameras on a polygon. So these are equivalent problems. You cannot find the minimum number of convex patches. You can compose it into, for example, trapezoids, but again, it's not going to give you the minimum number of convex patches within the polygon. But it's a very good question. So now, so this is how we motivated our triangulation algorithm, and any polygon. It may be a concave polygon. I'm not. Now we are in the domain of concave polygons, because we know convex polygons are guarded by one camera only. Any concave polygon, any simple polygon, is said to be a monotone with respect to a line. For example, if I draw a line like this, I can have a concave polygon like this. This polygon is said to be a monotone with respect to this line if any other line that is perpendicular to this line intersects the polygon. When it intersects this polygon, there is only one connected component. Okay? So, in other words, it's like this. My polygon is not monotone with respect to, for example, this direction. With respect to this line, my polygon is not monotone because this perpendicular line, when it intersects my polygon, there are two pieces this line intersects. When there are two pieces like this, it's not monotone with respect to this line. And we are particularly going to be interested in, we are going to decompose our polygons into Y-monotone pieces. And Y-monotone pieces is that with respect to the vertical line, if you divide your polygon into, if any horizontal line that intersects your polygon is going to intersect your polygon with one connected component. The intersection is going to be completely inside the polygon. Okay, so this is the definition of Y-monotone. And another property of Y-monotone polygons is that when you start from the top vertex, and there are two chains, left and right chains. So the top vertex has two incident edges to it, and you can say this one is the left side, this one is the right side. When you follow the vertices to the lowest vertex, during this traversal, you always go down or horizontal. Okay, you never go up. When this is in Y-monotone polygons, when you are you always in one chain you always go down or you go horizontal. You never go up. Okay, going up violates the monotonicity principle. So in a Y-monotone polygon, when you are following one of these chains, either of these chains, when you follow these vertices on this chain, you always go down or go horizontal. That's an important property of Y-monotone polygons. And what we are going to do is, given any simple polygon, we first, our triangulation is going to be composed of two different algorithms. First, we are going to decompose it into monotone polygons, monotone pieces. And after we have a monotone polygon, we'll be able to triangulate this monotone polygon in linear time. Given a monotone polygon, we are going to describe an algorithm to triangulate a monotone polygon. So it's going to be a special polygon which is going to be easy to triangulate. But first, how do we divide a polygon into monotone pieces? That's going to be our next algorithm. And we see that what we need to do is, if there are vertices like this, for example, this is a polygon. Let's look at this left-hand side. We are going to define vertices named turn vertices. For example, this vertex is really good because when you're going down, it's two neighboring vertices. So if this is V, this is U and W. If U and W, if one of them is at the top, at a higher point, and the other is at a lower point compared to this vertex V, we call this a regular vertex. It's a good vertex. It doesn't violate monotonicity. It means that we are going down, okay? But if both of its neighbors are like this one, look at this vertex. This vertex here, this time this is V, U, and W. Its neighbors U and W are both above V. So such vertices, we are going to call them turn vertices. And these turn vertices, we don't want turn vertices in a Y monotone polygon. So our goal will be to get rid of these turn vertices. How can we get rid of them? That's going to be the next thing. First of all, look at this vertex V. If somehow I connect this, now we are going to get rid of these turn vertices by drawing diagonals. Okay, by drawing certain diagonals, we'll be able to get rid of these turn vertices. Let me give you, and we are going to define, there are different types of turn vertices. We are going to label them as split and merge vertices. We are going to see based on the interior angle or based on whether both vertices are upside or upper or at the lower point of these vertices. So let's follow the book's example, which shows all these different types of vertices on the same polygon. Okay, so yeah, here's that polygon which contains many different type of vertices. So this is our polygon. Okay, so this is our polygon like this. Now, there are different cases, so let's call it, let me use different colors. Let me just label them. Merge vertex, start vertex, and end vertex, and split vertex. And this is a regular vertex. So where we have, so let's start ST. We are going to define 5 different types of vertices in any simple polygon. A start vertex, regular vertex, merge vertex, split vertex, and end vertex. And each, for example, this is also regular. So it's defined like this. A vertex is going to be a start vertex if both of its neighbors are below it and the interior angle the interior angle is less than pi. Okay? If the interior angle is greater than pi, it's going to be a split vertex. So split, merge. Okay? So if both of its neighbors are below it, it's either a start vertex or a split vertex. Okay? Since the both neighbors below it, and we are going to, this below and up definition comes from the fact that we are going to be using a plane sweep in which the sweep line is going to go from from this way downwards. So we are going to use a plane sweep algorithm to merge this polygon into monotone pieces. Okay, so if both of them are below the vertex, it's either a start vertex or a split vertex based on the inner angle here. And the merge vertex is if both of the neighbors of this vertex is above the vertex and the inner angle is larger than pi, it's going to be a merge vertex. And if the inner angle is smaller than pi, it's going to be an AND vertex. And during plane sweep, we are going to handle all these vertices differently. So let's see what we are going to do. So when we come to a split, for example, for a split vertex like this, as you can see, both its neighbors are lower than this vertex. If I can find a diagonal that connects the split vertex to an upper point somewhere else, it can either be this or this. Okay, if I can find a diagonal like this, it means what happens is that you see the split vertex immediately becomes a regular vertex in both parts of the polygon. Okay, because its neighbor, one of its neighbors is going to be up, the other neighbor here is going to be down, and in this polygon also, it's one of its neighbors is down, the other neighbor is up. So connecting a split vertex, finding a diagonal, so we need to make sure that it's a diagonal, it doesn't intersect any other part of the polygon. So if we're able to find a diagonal like this, what we do is we get rid of this split vertex and make it a regular vertex. And the same for merge vertices. For a merge vertex, if we can find a diagonal below it, okay, if we can find a diagonal below it, and if we connect this merge vertex with this diagonal and split the polygon into different pieces, what happens is that we get rid of this merge vertex into both of these polygons and it becomes a regular vertex. And there's a lemma in the book that says that if a polygon does not have a split or a merge vertex, it is a Y-monotone polygon. So if we can get rid of these split and merge vertices, if there are no turn vertices in our polygon, we make the polygon a monotone polygon. So our goal is going to be to get rid of these. And the plane sweep algorithm is like this. While we are going, so this is the sweep line. Okay, we have a sweep line, and our event points are going to be the vertices of this polygon. Okay, since and they are going to be sorted in terms of their y coordinates, and if they have equal y coordinates, we are going to process the ones to the left first. Okay, so we are going to do it like this. And now a question is, what is the complexity of building this event queue? Is it going to take n log n time to create this vertices ordered with respect to their y coordinates? Or can you do it faster? Because here you are given a polygon, means that the vertices are already ordered with some order, either counterclockwise or clockwise. So maybe making use of this path, this fact, but it doesn't guarantee, for example, these are ordered like this, but this comes first than both of these. So at turn vertices, the y sorting is violated. So I think still you may need to do n log n for the event queue, but I'm not sure. Let's think about this. I leave you as an exercise. Can you construct your event queue? I'm not giving it as a homework this time. I have a harder homework for you in mind. So the event queue is going to be consisting of vertices and with decreasing y coordinates. How fast can you generate this event queue? That's the exercise. It's optional, of course. If you don't want, you don't need to do the exercise. So our event queue is going to be static. Our only event point. We are not going to be generating new event points in this plane sweep algorithm. We are going to hop from vertex to vertex, going down each time. And our status structure is going to be a binary tree. We are going to be maintaining the edges of this polygon intersecting with the sweep line, again from left to right. And in the algorithm we are going to see that we are only going to need edges for which the inside of the polygon lies to their right-hand side. Again, this right-hand side is a global definition of right-hand side. For example, I'm not going to need to store this edge. I'm going to only store this edge, E1, E2, and that's it. Because we are going to see, while we are connecting the split vertices to a diagonal, I'm going to make use of the edges immediately to the left of it. So if there's an edge immediately to the left of it, it means that this edge, the polygon lies to the right-hand side of this edge. I'm never going to make use of these other edges. So for efficiency, you can actually get rid of some edges in this status structure, but if it's complicated for you right now, you may forget about it. Just consider our sweep line is very similar to the line segment intersection algorithm, stores these line segments that intersect the sweep line in a balanced binary search tree. So when we come to a vertex like this, we can query the line segment, the edge that is immediately to the left of this vertex. Okay, so I want to find this edge in this balanced binary search tree, and I want to find this one, but I'm not going to use the right-hand side. I'm always going to use the left neighboring edges. Now, in addition to the list of edges that intersect with the sweep line, I'm also going to use a concept called the helper vertex of an edge. Okay, the helper vertex is defined. So the helper vertex of, and for example, this is EI. Okay, if my sweep line is here, helper vertex is defined as the vertex that is closest to the sweep line. And also, if you connect this vertex to this edge, like this, with a horizontal line segment, this line segment is completely inside the polygon. Okay, so for example, the helper vertex of this edge is going to be this. Okay, why do we care about how are we going to use this helper vertices like this? If we find a split vertex here, if there's a split vertex here, for example, and the edge immediately to the left of this split vertex is EI, what I can do is I can connect the split vertex safely to the helper vertex of this EI. Because since it's the lower vertex, it's the closest vertex to the sweep line, the diagonal that I'm going to draw, I'm going to make sure that it doesn't intersect any vertex edge. But the thing is, the helper vertices of these edges are not static. They are updated dynamically. The helper, for example, at this point, at this event point, the helper vertex of EI is this vertex itself. Sometimes the helper vertex may be the upper end point of this edge. Okay, so if this is V1, if this is V2, when the sweep line reaches here, I set the helper vertex of EI to be V1. And only when I come to event point V2, I see that V2 is lower than V1, and it is immediately to the right of this EI. I don't need to even check whether this horizontal line intersects with anything or not, because I already have my balanced binary search tree. As soon as I get to this V2, all I need to do is ask, what is the leftmost edge, the left neighbor of this vertex V2? The left neighbor of V2 is EI, and all you need to do is set the helper of EI to this event point V2. Okay, so this is what we are going to maintain. We are going to maintain helper vertices of edges, and the helper vertices are going to be used to connect split or merge vertices to get these diagonals. We are going to use these helper vertices to define diagonals, and at the end, when the sweep line goes all the way to the end, our complex polygon is going to be chopped into pieces by certain diagonals. And these diagonals, now what we are doing is actually we are not triangulating it right now. We are dividing into some other polygons. And these polygons is going to have the property that they are going to be Y monotone. Okay, so I'm going to stop here today actually. Just let you digest this information for a while, okay? Since, the afternoon is official holiday today, so I'm not going to have the third hour, okay? So we're already afternoon right now. So I'm going to continue this algorithm in detail. I'm going to finish this monotone, decomposing a simple polygon into monotone pieces next week. And the other algorithm of triangulating a monotone polygon is very simple. If we have a monotone polygon, triangulating is going to be a very simple algorithm. I'm going to talk about these at the beginning of our next lecture next week. And also your homework for next week, okay? Actually, since we didn't finish this lesson, I'm not going to give you homework for next week, okay? So because we haven't finished this problem fully, so